Cross-cutting concepts serve as a bridge to connect the disciplinary core ideas of science: life, Earth and space, and physical science. They create a common thread from the beginning of the school year to the end, and across years of science instruction. Most importantly, cross-cutting concepts represent the major themes by which modern scientists consider content, providing access to a deeper understanding of the world around us. There are 7 cross-cutting concepts, as described in the NRC framework and Next Generation Science Standards. 1. Patterns. 2. Cause and effect. 3. Scale, proportion, and quantity. 4. Systems and system models. 5. Energy and matter. 6. Structure and function. And 7. Stability and change. Cross-cutting concepts come to life during class discussions. As students are engaged with sense-making discussions, explicit instructional strategies using cross-cutting concepts can help students learn how to extract meaning from data. Here, students are collecting and analyzing data from a heating and cooling experiment. The teacher supports the small group data analysis and sense-making with supporting questions about matter and energy, patterns, and systems.
I've been getting 23.
So far my graph, I've been getting the same as.
Yeah.
I've been getting 20. Going down and down.
What patterns are you noticing?
It's definitely stable at really hot points, and then it like kind of stops, and then
It doesn't really go down anymore.
Yeah, it can't like except for Caitlin. Hers is at 21.
Yeah, Caitlin's like really weird. Like after it gets out of the heat, if you let it sit for like maybe 2 minutes, it will make a drastic change. But then after that, if you just leave it at normal temperature, it will stay the same for the next like 6 to 8 minutes.
Consider our heat lamp. So that's our source of energy for heating the matter in our experimental system, right? If we're out in the world, what would be the source of energy for heating the matter in the world? Sun, okay? What do you think about your materials as compared to the other materials? Are all the materials getting the same amount of energy from our source?
Majority, it's just that some may have not been in the light as much as some others, so some may be less than usual.
They were all in the light for the same amount of time. So did they all get the same amount of energy to heat the matter?
Yeah.
Mm-hmm. But all of them didn't heat to the same temperatures.
I mean, they all are around the same.
Oh, they didn't?
Yeah. Like sand is less hot than air at 10 minutes. And so is water. I mean, water is like...
What do you think caused that matter to heat differently than the other matter?
I think because the particles in the other materials are more dense. Like at a normal state. Like sand is very dense and air is not. So it's not as heavy and it'll heat quickly.
Wow. What do you guys think about that?
Teachers can use a series of questions during a sense-making discussion to guide students to use a specific cross-cutting concept. As you watch this class, pay attention to how the questions support students' thinking about energy after they finish an experiment making waves with springs.
Let's think of the first activity that we did, where you tried to test different amplitude. And the question is, which waves have more energy, the high amplitude waves or the low amplitude waves? I'd like you to turn to somebody next to you who you don't usually work with and have a discussion with that person. Go ahead and pair up.
Like more kinetic energy.
Yeah, they were moving faster, so they had more energy.
Amplitude wave, if you go like really, really fast, it can be as powerful as a high amplitude wave, but it's less likely.
I think the high amplitude wave had more energy because the tape like in the middle was moving more, so you can tell that like it's moving more around.
Let's talk about the second experiment you did where we changed the frequency. What can you say about frequency?
I think the high frequency wave had more energy because it was like cresting more times.
and as an anchor, it was harder to hold it like still than the low frequency wave.
And like, also I agree with that because like I noticed that the high frequency waves there was like more per second or like more little waves occurred more often.
I need someone to go label this with high energy and low energy. Which one had more high energy and which one had more low energy? Why don't you tell us which one you'll label and we'll see if everybody agrees. So which is going to be your high energy?
Well, I'd say this would be high energy because there's more like kinetic energy.
I'm seeing a lot of heads nodding. Okay.
So should I just like write it here?
Yeah, great.
In the Investigations Guide, you will find embedded strategies for cross-cutting concepts. For grades 6 through 8, some cross-cutting concepts include a bridge icon. The bridge icon and teaching note indicate a place where you can link and integrate content between courses across the entire grade level. To use these bridge icons, visit the Cross-Cutting Concepts and Integration chapter to access prompts that help you drive student thinking to consider the way cross-cutting concepts support their science understanding at a deeper level between grade level courses.